All right. So yeah, I think I'll get going. So today for the game of the week, the swag, I'm going to look at a game called The Resistance, or the Resistance, I suppose, if you're French. And this sort of the stuff that I'm going to be doing today with regards to this game can be used in lots of strategy games, sort of like hidden information type games. So I'll talk about this game in particular, but again, a lot of these techniques can be used in other similar games. So how this game works is there's each player in the game is either a spy or a rebel, and the sort of the rebels are the good guys, and the spies are kind of sabotaging the rebels' plans. So you're trying to the goal of the game for the rebels is to try to figure out who the spies are, and obviously the goal of the spy is to try to not get found out and sabotage the missions. So how the gameplay works is that a subset of the players goes on a mission, and each player will secretly play a card to either pass the mission or fail the mission. Obviously, all the rebels want the mission to pass, so they always play pass cards, and the spies can actually choose to cause a mission to pass or fail. So even if you're a spy, it doesn't mean you're always going to cause missions to fail. And so that's how that works. So if 3 missions pass, the rebels win. If 3 missions fail, the spies win. But at various points, you can try to figure out who the spies are and get them out. Or just stop sending them on missions, basically, because then they won't sabotage. Another game that works kind of similarly to this, although it has way more complexity, is the Battlestar Galactica board game. It's an insane game, but that's one of the mechanics within it, that you don't know who the Cylons are, and then they can cause missions to fail. So this is the framework that we're working in. Spies can play pass or fail cards. Rebels always play pass cards, and you're trying to pass a number of missions. So obviously the number of spies depends on the number of players, but just in this case, we'll use a 6-player game, and so there's going to be 2 spies. So A, B, C, D, E, F are the 6 players, and 2 of those, we don't know who, are spies. So just to start off with, we could think about what the probability is that a randomly selected player from these 6 is a spy. And without loss of generality, we can just pick A to be talking about. So the probability that A is a spy, we could calculate that using the classical definition of probability, just by saying the number of ways to have A be the spy divided by the number of ways there can be 2 spies among 6 players. And so using sort of our good old chapter 3 techniques, there's only one way to choose A, and then the other spy is going to be 1 out of the 5 other people. So 5 choose 1. And then all divided by the total number of ways to choose 2 spies from among 6 players, which is 6 choose 2. That gets us a probability of 1/3. And because at the beginning of the game we have no other information, that probability will be the same for all 6 players. So at the very start of the game, the probability that any one player happens to be a spy is 1/3. Of course, we could have also just gotten that logically, right? Like if there are 6 players and there are 2 spies, then each person individually has a 1/3 chance of being a spy. So we could get it that way as well. Okay, I'm going to scroll down here a little bit. And obviously the 6 probabilities don't add up to 1 because there are 2 spies. The probabilities all add up to 2. So now, imagine that we send some spies on a mission. Not some spies, pardon me, some players on a mission. We're going to send A, B, and C on a mission, and the mission has failed, with 1 fail card being played. What can we do with that information? So this is an example of conditional probability. Once we have this information that A, B, and C have gone on a mission and it has failed with 1 fail card, that tells us some information. So then knowing that, conditional on that event, we can then reevaluate the probabilities of various players being spies. And it will change those probabilities because this gives us information. So basically what this tells us is that we know that at least 1 of A, B, and C is a spy. Not necessarily exactly 1, right? Because there could have been 2 spies and one of them chose to play a fail card and one of them didn't. There definitely couldn't be 0 spies though, because the only way to get fail cards is if spies play them. So the information that we have from this failed mission is that at least 1 of A, B, and C is a spy. So what we want to do then is reevaluate those probabilities of as any of the players being a spy. So again, without loss of generality, we'll consider player A. We want to know the conditional probability of A being a spy, given that at least 1 of A, B, or C is a spy. So that's what we're looking for. Given at least 1 of A, B, and C is a spy, what is the probability that A specifically is a spy? So we'll use the definition of conditional probability. It's the probability of the intersection of both A being a spy and at least 1 of A, B, and C being a spy, divided by the probability of the thing that we're conditioning on, at least 1 of A, B, and C being a spy. Well, for the numerator there, we can do something a little bit sneaky. Obviously, if A is a spy, it's true, like if that's the case, then the other event is automatically satisfied. Like if A is a spy, then for sure, yes, at least one of A, B, and C is a spy. It's automatically true. So if we were to draw the Venn diagram of that, A being a spy is like contained in at least one of A, B, and C is a spy. And so the intersection of those two events, is just where they overlap, which is just the event that A is a spy. I don't have my iPad working today, so I can't really annotate and draw a Venn diagram, but the Venn diagram would look like a donut. There would be an event completely inside another event. And so the intersection is the smaller one, the inside one. So the numerator there is just the probability that A is a spy. And then for the denominator, the probability of at least one of A, B, and C being a spy, the easiest way to calculate that is to use the complement. So we take 1 minus the probability that none of them are spies, and then that will give us that probability. So we'll take 1 minus the probability that none of A, B, and C are spies, which means that the 2 spies were chosen from the 3 other players, D, E, and F. So that's 3 choose 2 over 6 choose 2, and that gives us 1 minus 3 over 15, which is 12 over 15. So all together now we have the 2 pieces of our conditional probability. We have the numerator, which is just the intersection of those 2 events, which becomes the probability that A was a spy to begin with, which was 1/3 or 5 over 15. And then we have the denominator we've just calculated as 12 over 15. So when we put them together, we get a probability of, I guess, 5 over 12, which is 0.41666. And the same thing would be true for players B and C, the other 2 that went on this mission. So notice what's happened here. We originally, without any other information, had calculated the probability that A is a spy is 1/3. But now that probability has increased to 0.41666 because of this extra information we have. So A is a lot more suspicious now, and so are B and C, than they were at the beginning without any information, because we have this additional evidence that there's some increased probability of them being a spy because they went on a mission that was failed. We're still not 100% sure, of course. We're still only 41.666% sure that A is a spy, but we're a little more suspicious than before. We could do the same thing, actually, for the players that didn't go on the mission. So we think about D, E, and F, the folks that didn't go on the mission. We can do this exact same calculation. I'm not going to go through it in as much detail. But for this one, we want, again, the conditional probability that, say, D is a spy, given that at least one of A, B, and C is a spy. For the numerator, then, we need both of those things to be true. D is a spy, and at least one of A, B, and C is a spy. And for both of those to be true, we need D to be a spy, and exactly one of A, B, and C to be a spy. Not at least one anymore, because if D is a spy, then the other spy, there are only 2 spies total. So exactly one of A, B, and C needs to be a spy. So we can calculate that as well. D being a spy has probability, there's one way to do that, and then exactly one of A, B, and C being a spy, there's 3 choose 1 ways to do that, and then all divided by 6 choose 2. So all together we put that in, and the probability, the conditional probability of D being a spy, given that they didn't go on this mission that failed, is 0.25. And again, that's now lower than it was at the beginning. At the beginning it was 1/3, but now it's down to 0.25 because A, B, and C, are looking a little bit more suspicious. D, E, and F, even though they haven't done anything, are slightly less suspicious. And the same would be true for E and F. And then, of course, if you add up all 6 of those probabilities, the probability that A, B, C, D, E, and F are spies, those will all add up to 2. Because, again, there are still 2 spies. It's just that A, B, and C are slightly more suspicious now, and D, E, and F are slightly less suspicious. Scrolling along, let's now say that they send A, D, and E, so a slightly different set of players, on another mission, or second mission, and it also failed. What can we say now at this point? So we had that first piece of information that at least one of A, B, and C is for sure a spy. And now we have the additional information that at least one of A, D, and E is a spy. So A has now been on 2 missions that both failed. And that sounds pretty suspicious, but are we 100% sure that they're a spy? Not necessarily, right? It could have been like B was a spy and E was a spy, and then both of them failed the missions, and A is actually blameless. We don't know. But we can calculate the probability now that A is a spy, given that they have been on now 2 failed missions. So again, this is a little bit more complicated because we're sort of taking a conditional probability. We're conditioning on 2 different things. So we're looking for the probability that A is a spy, given that both at least one of A, B, and C is a spy, and at least one of A, D, and E is a spy. So again, we'll use the definition of conditional probability, and just as before, the numerator just simplifies to A being a spy, because if that's true, the other two events are automatically true. So the intersection is just A being a spy. But for the denominator, we can't just multiply the probability of this times the probability of this. They're not independent. So we actually have to evaluate how we could find that probability of both at least one of A, B, and C being a spy and at least one of A, D, and E being a spy. Now there's two ways we could do this. The easiest way, of course, is that A is a spy and then we don't care about any of the other players. It doesn't matter who that is. Or A is not a spy, but one of B and C is and one of D and E is. So there's two totally different ways that we could satisfy this event here, this intersection. We cannot, though, just take the probability that at least one of this is a spy and the probability that at least one of those is a spy and multiply them together. That would give us the wrong results because they're not independent. There's some overlap there. So we can do that. We can say, okay, A is a spy. Sorry, there's one way to do that. And then any other player is a spy. So we get this 5 choose 1. I'm sorry, highlighting all sorts of weird things here. Over 6 choose 2. Or at least exactly one of B and C. So there's 2 choose 1 ways to pick that. And exactly one of D or E is a spy. So 2 choose 1 for that. And then again, divided by 6 choose 2. So altogether, that gets us 9 over 15 for our denominator. And our numerator, remember, was 5 over 15, or just 1/3. So putting that all together, now we have a 55% chance, 55.5% chance that A is a spy. They're looking pretty suspicious, or sus, as the kids say these days. My kids are obsessed with the game Among Us, so, Mommy, you're sus. Anyway. So that's how that works. We can now say, again, it sounds pretty suspicious, but 55% isn't actually that high, right? It's like only just over half chance that A is a spy, given that they've been on 2 failed missions. We could also think about the other players, other than A, right? The 4 players who's been on one of the 2, but not the other of the failed missions. We could calculate that. I don't think I'm going to walk you through this entire procedure. It's very similar to what we've done before, but we end up with 1/3 again, which is kind of surprising. That was the probability that we had at the very beginning, without any information, of them being a spy. And now if they've been on one failed mission and not been on another one, now they have back to that same initial probability of being a spy. So just kind of interesting. They sort of being on one failed mission and not on another has sort of canceled out, I guess, that information. And then lastly, we can consider F, this person who has not yet been on any failed missions at all, and they're looking pretty exonerated. It's still possible that they were a spy, right? The spies could have been A and F, and then F would be a spy. That would be the only possible way for this to happen. And so that's possible, but it's pretty unlikely. So there's only like an 11.1 chance that F is a spy, given that there have been 2 failed missions, neither of which F was on. So that's kind of how this conditional probability can help us throughout a game, and then you can keep updating these probabilities as you go. So you have these, like now after these 2 missions, you have these probabilities. A is 55.5%, B, C, D, and E are 33%, and F is 11%. But then if another mission happens and it passes, let's say, then we can incorporate that information as well. So continuously updating the information by conditioning on the things that have occurred can help you figure out who's more likely to be a spy at any particular time. And you might get to a point where a probability of someone being a spy is literally 1. You might get some things might happen that it makes it impossible that for anything else than than someone being a spy is true. And so in that case, you would use that information to improve your gameplay. And you can do the same thing, of course, if you are the spy. You can do these calculations hopefully faster than your opponents can do them, and then you can use that information in terms of influencing how you play your cards and when you choose to make a mission fail or when you choose to make a mission pass. All right, that's all I wanted to say about that game. So next, I want to move on to talking about the machine learning idea of the week. This is one of my favorites, so I'm really excited about sharing this one with you. And actually, what we do today is going to be a little bit helpful for one of the toughest parts of the computer-assisted assignment, which was posted last night. So pay attention, and you might get a clue for that from this video. So what we're going to look at today for our machine learning idea of the week is something called the naive Bayes classifier. Remember what classification is. In machine learning, classification means taking the characteristics or observable evidence that you have for an object and trying to determine which category it belongs to. So whether it's, a spam or a legitimate email or a cancerous or a benign tumor or various other things. So we've got some evidence, and then we're trying to determine what category it belongs to. So essentially, any algorithm that's doing this is employing Bayes' rule to find the probability of being in a particular category given the evidence that we have. That's what the classifier is doing. Taking the evidence, using that to try to figure out which is the most likely category it belongs to, and then assigning it to that category. But using Bayes' rule, which we learned this week, we could write that as the probability of being in each category times the probability of the evidence given the category divided by the probability of the evidence. So I've just sort of used, in Bayes' rule, we use P of A given B is P of A times P of B given A divided by P of B. So that's what we're doing. We just have A being the category and B being the evidence. I may have said it backwards, but you get the idea. So this is just literally applying Bayes' rule. This is what we want, and that's sometimes called the posterior probability. And then this is how we calculate it using Bayes' rule. So we have the prior probability of the evidence, and then we have the probability of the evidence given it's in that particular category, and then the probability of being in that category to begin with. So we need all of those ingredients to do this. But the denominator itself can be difficult to calculate directly. So often we'll use the law of total probability, or sometimes called the partition rule, as just the sum over all categories of this component here. So the probability of being in category I times the probability of seeing this evidence given we were in category I. So that again is another rule that we've learned this week. I can't remember what Don calls it in the videos, whether he calls it the partition rule or the law of total probability, but those are the same names, two names for the same thing. So we can basically get this classifier by using Bayes' rule. Now, the simplest type of classifier, there are lots of different ones, is essentially assuming that if there are multiple pieces of evidence, like we're not usually just looking at one piece. If we're thinking about an email being spam or a tumor being cancerous, there's lots of information that we gather. So we're basically assuming that the pieces of evidence, if there are multiple ones, are conditionally independent. And conditional independence just means independence conditional on the category. So if we knew that something did belong into a particular category, we assume that the probabilities of the various types of evidence that they would show would be independent. Again, conditional on that category. And again, I've mentioned this before, but a really common application is detecting whether a message is spam or not. So we have multiple features that could be present with different probabilities depending on whether the message is spam or legitimate. So, for example, if you look at problem 22 at the end of chapter 4 questions, that's what I'm going to use as the basis for this, but I'm going to be a bit more specific about what this means. And we're going to see how we can calculate the probability using this naive Bayes classifier. So we're going to consider the problem of classifying messages as spam, and we're going to define the following 3 pieces of evidence. So there's 3 possible features that a message could have that might make it suspicious. One would be that it fails an RDNS check. Essentially, that's saying that the domain that it was said it was being sent from is actually spoofed. So what it says it's being sent from is not what it's actually being sent from. So something that might be someone trying to mask their actual email address when sending a spam message. That could be common. A second feature that might be present in a spam message is that the message is sent to over 100 people. So that might be something that's a little bit suspicious. And a third feature that that might indicate that a message is spam is that the message contains a link where the URL that it sends you to doesn't match the text that it says it's sending you to. So that's really common in phishing with a PH messages. They say, they write a link that looks like it's taking you to cibc.com or whatever, but when you click on it, it actually takes you somewhere else, which they've made a site that looks like CIBC, and then they trick you into giving away your password or banking information. So those are, again, 3 features that could exist in spam messages, but they could actually exist in legitimate messages too. Like, I have sent messages on behalf of the theater company that I'm involved with that say they come from the theater company's address, but really I'm sending them from my Gmail. So that's one example where it would fail technically an RDNS check, but it still is legitimate. I've also sent messages to over 100 people before. If I'm teaching a large class, sometimes I have to send messages to large numbers of people. And certainly it's reasonably common for people to have links that don't match the alt text. For example, like fill out this form, and then the words this form, when you click on it, takes you to a Google form or something like that. So none of these features are exclusively used by spam. Any of them could be used in a legitimate message. But the key is that they're more likely to be used in spam messages than in not spam messages. And again, we're going to use our naive Bayes classifier here and assume that each of those three characteristics are independent given the category. So that assumption may or may not be true, but that's what the naive Bayes classifier does. We're basically saying if we know that a message is spam, the probability of having any of these three features, A1, A2, or A3, are independent, conditional on it being spam. And similarly, if the message is valid, if the message is a legitimate message, given that, those three events are independent. And we're also going to estimate some probabilities that we need to do this calculation. So the probability that of these three features is 0.3, 0.2, and 0.1, given that they're spam messages, and 0.005, 0.04, and 0.05 respectively, given that they're not spam. These numbers are completely made up, just to be clear. These are not based on anything. They're just numbers to make an example. And then the other thing we need is actually a probability of being in each category to begin with. So we have here the probability of being spam in particular, or from the start, is just 25%. So 25% of email incoming is spam. That's also made up. I mean, hopefully it's not that high, but sometimes my spam catcher catches a whole lot of spam. All right. So now what we want to do is figure out the reverse, right? What we have is conditional information of features, these AIs, given the status of the message as spam or not spam. And what we want is the other way around. If we're trying to catch spam, we're going to look at the features and say, given these features, what is the probability that it belongs in the spam category? So we're essentially reversing the direction of conditioning. We have information about A given spam, and we want information about spam given the A's. So anytime you want to reverse the direction of conditioning, that's where Bayes' rule comes into play. So let's do it. Imagine that we wanted to find the probability of the message being spam, given it contains all three features. So what we're going to do is, I'm going to try to go like one line at a time here so I don't overwhelm you with math all at once. We're going to have, this is the definition here, the probability of spam given we observe A1, A2, and A3. So there's invisible intersection signs between there. So we have a message that's spoofed the from domain, sent to over 100 people with a link that doesn't match the alt text. Yikes. I don't know if I've ever sent an email like that, but it's possible. So if that's the case, that's what we're looking for. So we're going to apply Bayes' rule here, calculate the probability here by taking the probability of spam times the probability of all three of those features given that it's spam. And then again on the bottom, what we're doing here is dividing by the probability of having all three features. But we can't calculate that directly. We have to calculate that using the law of total probability or the partition rule, the probability of spam times the probability of seeing all those three features given it's spam, plus the probability of not being spam times the probability of seeing all three features given it's not spam. So that there is just employing Bayes' rule. And then to go from there, we need to apply our conditional independence. So here's where we're using the naive part of the naive Bayes classifier. We've been told to assume here that given the category, each of those features are independent of each other. So the probability of A1 and A2 and A3 given spam, we can write that as just the product of A1 given spam, A2 given spam, and A3 given spam. So that's what's happening here. We're using the conditional independence, the independence of A1, A2, and A3, given that it's spam, to break up the product, to break up the probability of that intersection into the product of those three probabilities. And again, we can only do this because we're making that assumption of conditional independence. We couldn't do that if we had a more sophisticated classifier otherwise. Same for the denominator, right? We could take the probability of this here and break it up into these three things here, and take the probability here and break it up into these three probabilities here. And I see a question, which I'm so glad somebody asked. On the bottom, the denominator there, is it the probability of A1 and A2 and A3? Yes, it is. But it's not the probability of A1 times the probability of A2 times the probability of A3. That's kind of weird because we were just told to assume that those events were independent, those features were independent, but they're only independent conditional on the category. So we're only assuming that A1, A2, and A3 are independent, conditional on the type of message. A1, A2, and A3, just on their own, unconditionally, are actually not independent. And that seems kind of weird. Like, how can events be independent if you condition on something, but not independent if you don't? And I can give you an example. Suppose we know that a message contains like feature A1, like it's sent to over, sorry, the from domain was spoofed. That alone, A1 being true, makes it more likely that it was a spam message, because 30% of spam messages have that feature and only 0.5% of not spam messages. So A1 makes it more likely for the message to be spam, which then in turn makes it more likely that A2 and A3 will also be occurring. Certainly not guaranteed, but more likely than if we didn't know that A1 had occurred. So the features themselves are not independent. A1 happening makes it more likely that the other ones will also happen. But we're assuming that if we know it's spam, so conditional on spam, those three are independent, and similarly conditional on not spam, those three are independent. So there's a difference between conditional independence, which is independence conditional on a thing, it's the same definition, and like sort of true unconditional independence. So a question again, so A1 given spam isn't necessarily independent of A2 given not spam. Correct. Yeah. I mean, technically you can't say things, you can't like combine events that are conditional on different things. You can't do anything with them. You can't like add them or multiply them or do anything until you like multiply something to remove the conditioning. But yeah, basically you have to be careful with this kind of conditional independence where we're basically saying if we know the category, then we can apply this independence and we can break up the the probability of this intersection into the product of those three probabilities. And same thing here. This is broken up into these three things here, and this is broken up into these three things here. What we're doing on the bottom here, this whole thing is calculating the probability of A1, A2, A3. But we could not just take the probability of A1, multiply it by the probability of A2, and multiply it by the probability of A3. That would be incorrect. Okay, thank you for asking those questions. I'm really, really glad you did. And then let's do it. Let's put all the numbers in. So here's a whole bunch of numbers. You can figure that out. They all just come from here. So this is our probability of being spam in the first place. And then these are the probability of those three features. Same thing down here. And then this is the probability of being not spam. And then the probability of those three features given that it's not spam. And altogether that gets us 0.995. So extremely likely, given all of these numbers, which are all made up, but extremely likely that if a message has all three of those suspicious features, extremely likely that it actually is spam. There's a very small chance, 0.05 chance, that we've misclassified a valid email as spam here. It's like a false positive, I guess. So it's possible, but it's pretty likely that we're going to say a message that looks like this with all three of those features is spam. So if you want, again, to sort of continue on, this is problem, which one? Sorry, problem 22 in the end of chapter 4 questions. There are some other parts that are similar. And now that you have this tool, this technique of this naive Bayes classifier, you can finish that problem on your own. All right. And again, I mentioned that this what I've done here contains a hint for the computer-assisted assignment. So in that, one of the things that we'll be doing is looking at test results that are sort of independent, conditional, or independent given the status of the person. So you can use this technique to answer that question. What part of this process is where the machine learns? So that's a great question. What I'm gonna scroll up here because that's where it happens. What the machine learning algorithm would do would look at this. That's assuming this is a supervised machine learning algorithm. So we have a bunch of messages with whether or not they have these features and an answer as to whether or not they were spam. So the machine learning would happen in determining what these probabilities are. All of those numbers would happen basically that's how those numbers would be obtained. So no, of course, if you knew all of those numbers somehow, then you wouldn't need machine learning to do it. But the machine learning is how those features are identified in the first place. Actually, it might be, again, you could tell the algorithm, these are the 3 features I want to look at. You tell me what these probabilities are, and thus come up with this classifier. But the cool thing is that the machine learning algorithm itself might find other features that we as humans might not think to look for. So if we give this algorithm a whole bunch of messages with lots of different features, like tons of different things, and we say, okay, these were spam and these were not, build me a classifier to tell me what other messages are spam or not, that's where the machine learning happens. So it's going to identify features, and again, the best features are ones that have a very significant difference between this probability and this probability. Also, again, here we only have 2 categories. Of course, we could have a classifier with multiple categories. So the machine learning algorithm could also figure out what the categories should even be, and also what features to look at. Okay, another question. Does it figure that out by just storing number of times this happened and number of times it was spam? Essentially, yeah. It's sort of just looking at all of this data and figuring out what's the conditional probability. Like, of the spam messages, how many of them have this feature? Of the non-spam messages, how many have this feature? And then the best features, the ones that are going to be most predictive to improve the accuracy of the classifier, are the ones that have the biggest difference between the prevalence of that feature between the 2 different categories. Again, this is probably the simplest machine learning algorithm there is. So they get more complicated, of course, but that's kind of where that comes in. So you could probably code this, actually, honestly. You could probably, if someone gave you a bunch of data, you could write something to do this without even needing any sophisticated tools. What language? I don't have a favorite. I honestly, I don't know. I would start by just Googling and seeing what other people are using, honestly. Like, any code that I've ever written is started based on looking at like other things that people have done and then just modify it for my purposes. So that's what I would suggest. Like, Python is great for a lot of relatively simple things. There's more complicated stuff out there, but it depends on what you're trying to do. So I would, I would say, see what's out there, see what's already been done, and then try and modify from that, rather than trying to start from scratch. Actually, that's a good segue, because I think what I will do, I still don't see any questions from Piazza. I think I'll just show you a little demo of how RStudio works, which is a development environment for the statistical language R, which you will need to be using for your computer assisted assignment, which again just was posted last night. So you start dealing with R by just downloading R. Like, that's what you want to do. So I would go to, there's instructions for how to download it. Just go to Google R download, go there. And then you can find the following website, R download, just R project. That's a great place to start. And download. You want to download from CRAN, which is the Comprehensive R Archive Network. It has nothing to do with cranberries. So pick your favorite country. I recommend Canada if you're in Canada, but if you're not, whatever country is appropriate. There's lots of different mirrors that you can download it from. I usually go U of T, just because it's the closest to where I am. And then you can download R for whatever operating system you use. So I use Windows, so I would download R for Windows. So you install that. It's updated. It's an open source thing, so it's updated fairly frequently, and you can there's not huge massive changes between the versions, but you probably want to start with the most recent version at the start of the term. Nothing astronomical is going to change between now and the end of term, so you don't have to update it anytime. And then the other thing that you should do is download RStudio. So again, just Google RStudio download. I wouldn't bother memorizing where to find that, and then go here. And then similarly, choose whichever version you want based on your operating system. And I'm sure there are paid versions, but you don't need a paid version. You can use a free version. It's great to use. So once you do that, then you can open RStudio once you install it, and RStudio looks like this. Up here on the left is where you can type code. And it's also, you can open files. So like here's a file, this is the file that's posted on Learn of the different things that you can do. So you can just type code in here and it doesn't run it, it just sort of sits there. If you want to create a new one, you can just create a new R script. So a new R script is just a blank file that you can type code into. So that's pretty awesome. Down here is where the commands actually get run. So the bottom left here. So if you want, you can type stuff directly into this console window down here, like 1 + 1. Hey, it's 2. But the cool thing about this though is you don't usually type stuff into the bottom window down here. You type it up to here, and then to tell R to run the commands, you can either just click like run, or like there's a button here that says run, or you can run an entire section at a time, or just I think it's Shift Enter. Yeah. So Shift Enter, or sorry, Control Enter is what I did. Control Enter will take the code that you wrote up here and put it down here and run it. So you can do a whole bunch at once too. So you could like say all of this and then Control Enter. It takes all of that code that I've written at the top and it puts it down here and runs it all. And so this can be really nice because if you rather than typing code into the bottom over and over and over again and having to make corrections, you can type it all up here, make corrections until it's perfect, and then run it all at once. So that's the idea. The other thing that happens is, so on the right-hand side, we have 2 more fields here. This at the top right here is really useful for kind of debugging and figuring out what's going on. Whenever you create an object in R, it's going to appear here. So I'm going to just start a random sheet here. You can create objects in R and then assign them to values. So like you can say X is the number 5. Okay, that hasn't done anything because I haven't run the code, I've just written it. So if I run this code here, run it or Control Enter, then you can see down here it's got X is 5, and then I asked what X is and it told me it's 5. Surprise, surprise. But now look what's happened. Over here, it now has in my environment, which is like all of the objects that have been created, it has the name of the object and then its value. So anytime you create something, it's going to store it here, and then you can see its current value. So you can also like reassign it. So X has been created now, but if I wanted it now to be 4 instead of 5, sorry, and I run that, there we go. Now you can see that it's updated here. So this object X now has the value 4. So that's how that top right thing is useful. And then finally down here is some useful stuff. The most useful thing maybe is the plots. So if you want to create a graph or a plot in R, it will appear here, and then you can copy it and save it and put it into your assignment. So maybe I'll actually grab some of the code from the tutorial here rather than write my own. There's lots of functions that are built into R. I'm not going to talk through every single one, but like square root, logarithms, base E. This is automatically base E. If you want to do log base 10, you have to specify base 10. You can do exponents. R stores things as vectors. So that X that I created is a vector of length 1. But I could also create, say, let's do these lines here. I'm going to run those. So now Y is a vector. It's a sequence going from 0 up to 10 by 2s. So it's a vector, like a column vector. It's written sideways, but every vector is a column vector in R of the numbers 0, 2, 4, 6, 8, 10. And then again, you can see up here on the right, it's now we have this value Y, and it's a numerical column vector, dimension 1 by 6, 1 row 6 columns. Sorry, 1 column 6 rows, 0, 2, 4, 6, 8, 10. So sequence lets you do a sequence. Rep lets you repeat the same thing over and over again. So if you wanted, say, like a blank vector of zeros, you could just say like Y, left arrow, rep 0, 100. That will create a vector of length 100, all of which are filled with zeros. So you can create vectors really easily in R. There we go. You can also like put data together. So I'm going to do this here. Just run those. And then frame some data and sort of like put them together into a data set. So now that's kind of like looping data together. So it has these 2 objects, X and Y, that are 3 element vectors. And the data set is the combination of those 2 together. And then you can do some stuff with data. You don't have to only store numbers, of course. You can store strings in R, so that you could have a vector of strings, however you like, and you can do all sorts of neat stuff with that. I'm not going to go through all of this. What I wanted to do was talk about plotting. Go down here. Oh. I don't see it, so I'm just gonna type it. So I'm gonna type it down here. So if we want to plot X and Y, I want to see what happens. Ta-da! Pretty boring looking plot here. So we have X on the X-axis and Y on the Y-axis. Whatever you put first goes on the X-axis. Whatever you put second goes on the vertical axis. And a plot by default is a scatter plot. So if you want to make it a line plot, you could do that as well. X, Y, and then you would say type equals L for line. So that's a line plot. So then instead of being 3 points, it's actually connected them with a line. I'm sorry, this is a really boring set of data. I could have made up some more exciting stuff. So you can see how to plot graphs in R. They automatically will label the axes for you and put the different gradients, however it thinks will look good, but you can actually specify that. Like if you wanted the y-axis to go from 0 to 10 instead of from the 2 to 6 here, you could specify that. You can also add a title to your plot. You can do all sorts of things like that. So if I wanted to add a title, you say main equals my plot. Like that. It's kind of boring. There we go. So now it's there. And again, like if you wanted to have different labels for your x-axis or y-axis, you could do that as well with x-lab and y-lab. So lots of different ways that you can do plots. And then to save the plot, you can either export it as an image or a PDF, or just copy it to a clipboard and then paste it wherever you like. So that's how to use plots in R. Just looking at other things that might be useful for you. Again, I strongly recommend you to have a look at the R tutorial that's posted, because it's going to have a good overview of the tools and techniques that R has built into it. The other cool thing that R has built in, because it's a statistical programming language, is it has all of these stats built in. So when we get to chapter 5 and we learn about all of the different random variables that there are, all of those are built right into R. And it's also really, really good at doing simulations. So it's easy to sort of simulate from various distributions, and that gives us the ability to sort of empirically investigate probabilities and estimate probabilities to see if we're we've calculated them correctly, or to get sort of another way of calculating a probability. Alrighty, I think that's all I want to show you for now about R, just how to do plots and sort of how to work with it. Once you have an R script here, you could save it, of course. The other thing, actually, I want to show you one more thing. If you want, this is completely optional, but a really slick way to make really nice output is R Markdown. So an R Markdown file, I'm just going to call it untitled because why not? When you create an R Markdown file, again, you go to New, and then instead of R script, say R Markdown. It'll tell you what it looks like. And it just has a little bit of an instruction on how to use it. It basically, you can use LaTeX within it, and you can put R code into it, and then the R code will be outputted, and any plots or values that R has calculated will also be output. And then when you're done, you can just say knit to PDF. Basically, R Markdown is a really neat way to get the text that you want to write integrated with the R code that you want to run. But again, you do not have to use it. You could just copy and paste your R code into Word or your other favorite editor, copy and paste your plots into there as well, and then submit that all as well. That's all I wanted to say about R. If there are questions, of course, you may have some after you look at the tutorial material. I can do more demonstrations next Friday, or even the Friday after, although that'll be kind of late because that's literally the deadline for the computer-assisted assignment. But I'm happy to show more R stuff later on if that is interesting to you. How long do you think the computer-assisted assignment will take? That is a great question. It's 2 questions. Last term there were 3 questions, and we sort of thought we wanted to make it a little bit lighter. I think it will depend on how quick you'll get up the learning curve of using R, But many of the questions don't require R. So in fact, both question 1 and 2, there is some significant sort of theoretical work that are maybe like a little bit more difficult than the quiz questions that you've been seeing. They're sort of like at the level of the end of chapter questions, maybe a little bit on the more difficult side of those. So those I think won't take too long. And then figuring out how to get that into R might take about another sort of half of the time. So, I mean, we're not expecting you to spend a huge amount of time on it. But I hesitate to give a number of hours because it's going to depend so much on each person's individual knowledge and facility with learning a new language. If you have questions about R in general, like we're not going to answer questions about how do you do the assignment with R, obviously. But if you're having trouble figuring out how to do, like how to use R, how to get set up, for sure, feel free to post on Piazza. And I do encourage people to like, at least even this weekend, I know the assignment's not due for 2 weeks, but just make sure that you can get R working. Like download it, open it, make sure that you can like run 1 + 1 = 2. If everyone does that, at least, that will be a huge hurdle to get over. Just opening it, downloading it and opening it and getting it running is the biggest hurdle to get over, just to start using it. But yeah, I think the questions are hopefully reasonable. That some of them are a bit tricky, some of them are a little bit hard because you've got like 2 weeks to work on it, and it'll test your knowledge of a lot of different things that we've talked about in chapters 3 and 4. The focus is on chapters 3 and 4. So you have now all the material that you need. There's no new fancy stuff in chapter 5 that's going to help you with this assignment. But the how to do it in R, that might be faster for some people and that might be slower for some people. In fact, some people might find the R parts easier than the theoretical parts. And that's okay too. You can do it in R and then use the R to sort of inform how your theoretical one, or evaluate whether you think your theoretical one is correct. Cool. Thanks for asking. And I'm sorry I didn't give you a solid answer, but it depends. Cool. Oh, got a question. Can we submit our script files directly to Crowdmark, or are we supposed to copy it to a PDF or Word? Thank you for asking that. You definitely should not just submit your R script. But if you use R Markdown, and you sort of fill in all of the sort of theoretical parts, you can knit that to a PDF and then submit that to Crowdmark. But again, you don't have to. You could just, probably the easiest way to do it would be just copying it to a Word or a PDF, or turning it into a PDF. So we have posted some sort of templates that someone made, or Audrey made up, of like what it could look like. You don't have to follow that exact format, but there's sort of like a theoretical part, and then she's pasted like, this is my R code, and then this is the answer. So making sure that you're giving us both your code, what the output was, and then also specifically answering the question. So if you just put your code in the output and then don't say, therefore the answer is blah, you likely will not get full marks. My advice always is, make it easy for the TAs to find your answer, right? That the easier they can find your answer, the happier they are, and happy TAs give higher marks. So do the work, and then when you're writing it up, just copy the commands that you used and also the output, and then say, either circle it or have a sentence at the bottom like, therefore the answer is blah, and then put a box around it or bold it or something so that the TAs can find it easily, because the easier they can find it, the happier they are, the higher mark you're going to get. So thank you for asking that on Piazza. Have a great weekend, and good luck on finishing up your collaborative assignments, and hopefully please just download RStudio, open RStudio, type 1 + 1, hope that you get 2, and then close it. If everyone does that, I will be happy. That would be a gift to me if everyone just gets it working, so that when you finally do start working on the assignment, you don't have to get over that initial hurdle of having used it. All right, have a great day, everyone. See you next week.